Thank you very much. Thank you, Flair. It's a big challenge for me. This is not the first slide. There is one before. So it's a big challenge for me to stand here and give you in 12 minutes an introduction to the brain, and especially what we plan to do and what I feel is one of the really leading projects in the world for the next 20, 30 years. So I want to introduce it to you. And actually, because this became the first one, yeah, so this is me, and I really want to discuss the 100 years from now on. As Fleur said, it's the past was very interesting, but this is the past, and I think we should be connected to the past, but should really plan the future, and I want to show you what is our planning for the future in terms of brain research. So what do I do? Okay, so let me start with a story, a real story that happened to me, and I think this story will help you to understand what I'm saying. So recently we decided to erect a new journal for kids. It's called Frontiers for Young Minds. And the journal is very unique because the journal is the articles are written by scientists, top scientists in the world. We already have 200 articles written for kids, but the kids are our reviewers. So they decide if the paper will go into the journal or not. This is an internet journal. It's for your kids. So the idea is that we write, scientists write, but the kids decide whether the journal is good enough or not, or the paper is good enough or not. So this is Frontiers for Young Minds, and we are covering many, many directions. We are trying to cover energy, renewable energies, and brain, and health and diseases, to explain to children what we are doing so that they will be prepared for the future of the world. That these children should know where they are going to, automated car, robots, avatars, and so on. So I wrote this paper some 5 years ago. It was the first paper written to this journal, and I was rejected twice by this young lady. So this is a lady I don't know. We are not allowed to show her face, but she's age 11, AB, and she said, with all respect, Professor Segev, I don't understand what you do. I reject your paper until you explain it correctly. I tried, seriously, I tried once. I was very pleased to be rejected by a kid, because the whole idea is that the kid will decide if it cuts the level of other kids. Otherwise, it will be my paper, but nobody will read it. And she asked me 3 questions about brain simulation. And these are the 3 questions that she asked me. What does it mean to model the brain? You didn't succeed to explain it good enough to me. Why do you need to model something that already exists? So there is a brain here, she says. Why do you need to model it? It's already there. It's an excellent question, but I did not explain it because I took for granted that she would understand it. I'm used to write to scientists, not to kids. And the 3rd question was, what do you learn from this modeling of the brain? So that's exactly what I'm trying to tell you now. So this kid helped me a lot, really, to explain it to you. Okay, so recently I was visiting Spain, and this is Queen Sofia of Spain, and I told her, and this is the truth, that the whole brain research started, and what we do today is really an extension of what Ramon y Cajal, so Santiago Ramon y Cajal that you see there, was the greatest anatomist. He got a Nobel Prize in 1906, and he did that. What he did is really started to paint, draw neurons, nerve cells. He was actually the first one to note the brain is built from nerve cells. Nobody knew that the brain is built from cells. They thought that it's a different organ, that we feel, and that we love music and opera and so forth from something else. It's not cells. He discovered the neurons, and he started to reconstruct the brain, so to speak, by drawing it. He just drew the brain, pieces by pieces, cell by cell, neuron by neuron. And he was also very poetic. I like this way of describing the brain. Ramon y Cajal called neurons the butterflies of the soul. So now you see the butterflies of the soul. I'm not allowed today to write a scientific paper with such a poetic way of describing the brain, but I still am trying. Butterfly of the soul. So you see the butterfly of the soul of Ramon y Cajal. And what we are trying to do today is to really extend Ramon y Cajal to new directions, into the following directions. So first of all, we want to reconstruct the brain digitally. So it's not going to be on a paper, it will be in the computer forever. You can always will be able to look at our data that we generate today, all over the world, but of course us including. Then we want to use the digital data to simulate the brain, and that's the difficult thing that I need to explain to you and to Abby, 11, 12, what does it mean to simulate the brain? And what then I earn from simulating the brain? Let's say that I have a brain simulation. What does it mean? What can I do with it? How will it help me to understand the brain? And I will show you that we can understand the brain through the simulation and then design new technologies based on the brain. Brain-inspired technologies. So let me start. You are now listening to a nerve cell, individual nerve cell in your brain that is now electrically firing. This is the activity of a single cell, electrical activity of a single cell, and of course you have much more than one cell. You actually have 100 billion nerve cells in your brain. Each one has this kind of electrical code, electrical activity. So because it is an electrical device, because the cell is an electrical device and chemical device, we can write equations that describe this electricity. Because we understand electricity, we understand chemistry, so we can write equations. So I'm going in the next half an hour to explain you the equations. So this is the equations we use in order to describe electrical activity through current flow, electrical activity through current flow of ions, charged ions, and eventually they generate this phenomena that you heard, tak, 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 tak. This tak, 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 tak is electrical activity of a brain unit. And of course, when you have a philharmonic of tak, 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 you have a huge brain activity which represents my talk, your feelings, everything. You know there is nothing else. There is only brain activity. There is no magical aspects. It's brain and chemical activity that generates everything, and that's what we want to simulate. So I'm not going to go through the equations, but we have very good mathematical description of the activity, both chemical and electrical, in the brain. Because of that, I can now mathematically simulate, and I hope now that you will understand that, because I have an equation, I can simulate and mimic, very, very closely, mimic the activity of real neurons. So the brown activity, these are spikes. It is called spikes. So tac, tac, tac. This is from experimental results, recording from brain cells. And the green one is our model. You can see how close the green spikes, the green electrical activity simulated in the computer is close to the brown activity measured in the biology. Okay, that's called brain simulation. In this case, it's a simulation of a single cell, one cell. But of course, if I can simulate a second cell and a third cell and then connect them chemically with an equation, I can simulate the whole brain. And I'm not leaving anything. That's the whole brain, if I will get into it, and we'll discuss it in a second. So that's the idea of simulation, using mathematical equations to describe a biological phenomenon. We decided not long ago, together with a group in Lausanne, in Geneva, to try to simulate a piece of cortex. So, you know, below your skull, you have cortex, this kind of a folded tissue, and we are trying to look at 1 cubic millimeter here. So this is 1 cubic millimeter. It's the size of a pinhead. It's the size of a pinhead, and in this size of a pinhead of a cubic millimeter, this is your skull, and just below 1 millimeter deep and 1 millimeter into the wall. So 1 cubic millimeter, it's about 100,000 cells, nerve cells, and about 40 million connections, synapses. We want to simulate all that just as a proof of concept that we can do it. And indeed, we succeeded to do it in the last year or two, and we succeeded to simulate fully a whole piece of a cubic millimeter of a mammalian cortex, in this case of a rodent. We'll talk about human brain in a second. So we put everything into the computer. Here is the computer. This is a big computer in Lugano. It's a huge IBM computer. You can solve the equations of 40 million synapses and 100,000 of cells and 4 kilometers of wires in this kind of circuit, and we did it. So this is how a cubic millimeter in your brain looks like. Okay, this is a jungle of nerve cells, very, very complicated circuit. You can see the circuit, you can see a cubic millimeter, you can see all these wires connecting to other regions and also within. And as I said, within we have 100,000 cells. This is now a voyage in the computer to your brain. I mean the brain of rodent. But it's not very far from your brain. Otherwise, all the diseases we develop on the rodent, all the pharmacy, all the pharmaceutical drugs that we develop on this brain works on your brain. So it could not be too different, otherwise it won't work. So this is a 1 cubic millimeter, and then we can see that the building is also inspired because what you see in our building, and I hope you will visit it, is exactly a rodent brain. Seriously, these are the cells that we reconstructed. These are cell by cell reconstructed. There are no 100,000 cells there, but each cell is separate. So this also, the brain is also an inspiration for a wonderful building that I hope you will meet soon. It's just opening now, and we are moving there. Brain-inspired building. And we not only can, of course, build it anatomically, but we can also simulate it. So I can now, in the computer, give a pulse, a stimulus in the computer, electrical stimulus in the computer, and the circuit starts to be active. It's not a passive circuit. You activate it, and the circuit starts to fire spikes, 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 dynamics, and so forth. It's a real circuit mimicking a circuit in the brain of a rodent. And this is another activity of another circuit, and you start to ask questions about what will give rise, for example, for this kind of electrical wave in your brain. You know that your brain is active, and when you sleep, there are electrical waves of one type, and when you don't sleep, there is an electrical wave in another type. So now we are trying to understand the brain activity using the computer. And for example, this is the first result. What did we learn anew? What is new by doing this simulation? The first thing that we learn, it's extremely interesting. I just published it in Nature just a few months ago, and this is extremely interesting. So when you build a building, from a cell, another cell, and you pack these cells together into a cubic millimeter, like here, you can ask what is the structure underlying this building, because you just put 1, 1, 1, 1 and pack them, but there are emergent structures. And we use the very sophisticated mathematical graph theory to find out that the brain, your brain, the brain of them, and something we did not know before, that when you pack so many trees together, you get a very special structure innately in your brain. This is innate structure in the brain of mammals, in the cortex of mammals. For example, some cells serve as hubs. There is other cells that interact between other, and that they generate a rich club. So if you are a hub and you connect to another hub, you become a rich club. Rich people like to meet each other. And these rich neurons like to interact with each other. And this is extremely important. Why? Because if a disease attacks a particular cell type, like a hub, if there is a disease that attacks hubs, the whole circuit collapses. It can't function anymore. It's very important to understand the structure of the brain at that level of resolution, and we did not know it before we build it. So building something makes you understand this something. But that's very new. So there are hub neurons. We know who are these hub neurons. We know how to target them, but we also start to understand how to protect them from an attack. We want to protect the hub neurons from attack because these are the key neurons that if you will destroy them, the whole system will collapse. This is a new result. Another new result using this simulation is we are starting to understand epileptic seizures. So you are trying to understand in your simulation what are the conditions, what are the parameters that give rise to epileptic seizure. You see now epileptic seizure in the computer. It's not that the computer becomes epileptic. It's the simulation in the computer shows you what are the parameters for this group of cells, for this loci, to become epileptic and spread all over the brain. This is a new understanding that came from the simulation. Now we can also use the circuit and just discuss it with Amnon Shashua recently from Mobileye. So we can take the circuit simulation and teach it to drive an avatar car. That's what you do when you drive a car. After all, you use your brain to drive a car. We're trying to understand what are the parameters in the circuit that needs to learn to drive a particular car. Because eventually, we do it in many, many ways much better than anything else, and we want to understand how this circuit learned to drive a car or learn to do anything, and we are already successful in using the circuit to drive avatar cars, robots, and so on. The next challenge, and I'm going to end by that, is of course to go to human. I praise the mouse in many ways, but of course there are some differences between human and the mouse, because the mouse didn't come to my lecture and you did. So we are trying to understand the mouse and the human as well. So this is the brain of a human, and this is a tissue that had to be taken out because of tumor here. So you take the cortex, and this is a piece of a cortex from human taken in Shaarei Tzedek here, in the hospital here, and it's done very rarely, actually, that you take a tissue in the hospital, you take a tissue in the hospital, and you use it for physiology, to record the cells. Just to show you, so this is the tissue taken out from a patient here, and this is the brain of a mouse. You see that the tissue that is being taken out is bigger than the whole brain of the mouse, and we are starting to use this tissue, the live tissue, that we can hold inside a plate for 3 days alive, a separated tissue, but alive with spikes and chemistry and synapses and connection and activity, and use this to better understand human. So this is the first result. We didn't publish it yet, but it's the first result. These are human cells reconstructed from real human tissue, but they are not only reconstructed, they are also active electrically. So our next job is to try to reconstruct in the computer a whole human brain, which requires a lot of computational effort. So let me end by saying that I'm thankful for Abby, hoping that she helped me to understand and also tell you how to tell the story of why do you simulate the brain and what do you learn from that. I also want to tell you that we just came on the 1st of June, due to a very nice donation from the Drahi family, to translate the Frontiers for Young Mind to Hebrew. It just came out. We already have 2 million children in America and England reading this, but now we are starting in Hebrew. So that's the first article in Hebrew, and came out. We have now 30 in our system, and it's about memory in this case. So we are now moving. The next translation is to Arabic, so all Arabic children in the world will know what brain research is about, because we need to understand the future. So that's one challenge, to nurture the children, but we also nurture the PhD students, because they are those who will really lead us to the future. I'm very proud that in our center you have 90 PhD students in brain research in all fields, and 50 of them are women. So thank you very much.